Hi, and welcome to this value stream mapping webinar or tutorial. Basically, what we're going to go through here is we're going to construct a current state value stream map. I'm then going to take you through some of the guidelines, if you will, for constructing future states, some of the lean considerations and guidelines, and then we will move into constructing a future state map. Just a couple of things to bear in mind. The broadcast, this webinar will be posted afterwards and will be available through Moodle. In addition, there is a Learning to See ebook available. The link is on Moodle also, and basically this tutorial example, if you will, is based on that particular model, so it's well worth going afterwards and having a look at that book as well. Okay, so if we want to get started, using the value stream mapping tool is fundamentally a way of understanding how the production environment currently runs. As with most things in terms of how we deploy lean, it's very important that we understand where we're starting from. So this is about establishing a current state or a baseline, if you will, from which we then design our future state. Another point to bear in mind is that value stream mapping is typically done for either an individual product or a family of products. It doesn't apply across the entire organization, the entire operation, for example. So one of the things that needs to be done before you start commencing a value stream map is to actually identify the appropriate product or product families which will fall within that value stream. The method for doing that, as you can see on this slide here, is typically we create a grid with the products that we might have running down the side, and across the top we have the process steps and the equipment that might be used. You can see again here that two of these have been identified as broadly similar. So again, these ones here that I just highlighted, you can see they're going through the same process steps. So naturally, they would make sense to look at trying to manufacture those together. The others would potentially be three separate product lines, or could be from another combined product line with some variation accommodated within them. We'll get into all that later. However, the point to remember here is that it is important to clarify and to identify which products or product the value stream is going to be applied to. Okay, this is just a sample picture of a value stream, just to give you an idea conceptually of what it looks like. There's a particular format, if you will, to them, and that is that typically in the top half here, we document and capture the information flows. So it could be forecasts or orders coming in from the customer, suppliers receiving orders or forecasts from ourselves, and the production schedules, etc. Typically then below the line, we would have the actual production process that occurs. So you can see these various product production steps, if you will, or processing activities. And then we capture information about those. So if you will, the top half of this map looks at information flow, and then the bottom half looks at the material flow and the production processes that go into that. That's just a quick visual of what we're going to be constructing, if you will. Okay, so the current state drawing, remember, it's the starting point. We start with the current state. The intention is to then move on and develop our future state. So this is the first step on the path. Some of the things that we do need to capture, we need to get the material in the information flows. We have specific icons that you've seen in the previous picture, and there are lots more of those that you'll see as we go through this. And then we typically will start with the door-to-door flow, what's going on within our own building. Again, don't use standard times, don't use systems information. You should go and capture this information real time, either observing the work that's being done, counting the inventory that's physically in place, or such like. Okay, so in terms of what do we map, here's a set of sample data, if you will. Let me just enlarge that so you can see. So starting out with some customer information. The requirements. So we have their demand information, the breakdown of what the mix might be, when they're running, how they want the materials brought in, how frequently they're getting them. And similarly, some of the information regarding their own work time. They're doing 20 days a month, 2-shift operation, 8 hours, and so on. So the point here is that this is information that's relatively easy to capture, should be readily available from our customers. Let me move on to the next slide, and you can see we've actually started to draw things here. So let me just enlarge this a little bit. We have our customer, we have their demand information, the way the product is shipped, the number of shifts they're working, and their daily shipment. So already, hopefully you're beginning to see that data we have, that we're able to start mapping this maybe. Capture some information here now in terms of how the information flows and some of the processes that are involved in manufacturing. And so here we have Acme's processes telling us they've got a stamping operation, then a welding, an assembly, and then stage is shipped out to the customer. We're making lefts and rights and have to switch between them. And here's some information then in terms of how we receive our forecasts, how we send out information to our suppliers, and how the production floor is scheduled. Again, the point here is that this information is relatively easy to capture. So some of the specific information about the actual operations, and this is the type of information that typically you would need to go to the shop floor and physically observe what's going on, physically count the number of pieces of material that are there, etc. However, it is readily available. So we look at the stamping operation, a couple of pieces of information. It makes parts for many products, so it's not just for these 2 products. And then we have information about the cycle time, the changeover time, reliability, and the observed inventory, so the amount of information that was physically counted. Similarly, if we look at the spot weld workstation, we have the same type of information, looking at cycle time, changeover time, and the inventory that was there. Same for the second operation, that cycle time and the inventory that's sitting there. So that process basically continues through the assembly operations as well. And there you have it. We now have pretty much all of the data we require to move forward. So if we now start to look at the value stream map again, you'll see we already had our customer information and this one weekly delivery. Now we can start to put in the individual process boxes for the processing steps that we've outlined earlier. If I fill the first one in, for example, you can see, let me just enlarge that a little bit and we can have a closer look. So the stamping operation, it's a 200-ton press. There's 5 days worth of inventory in front of it, and there's 4.5, 4.6 left and 2.4 right. Sitting after it, we have a cycle time information, changeover information, and uptime, which we had already captured. So it's really just a case of putting that onto the map. Again, there are four additional processes that we need to do that with. So rather than go through them one by one, you can see the model. Essentially, we've now captured the inventory that's sitting between all of the stations, and the processing activity times, the cycle times, changeover times, machine uptime, and so on for all of the different processing stages. Okay, so we're well on the way at this stage. And again, all the data that we've been using has, if not readily available, it's certainly been accessible. And while it can take a little bit of time to go and gather it, it's not physically awkward or difficult to get to. Now we can start to look a little bit more around the information flow of the value stream. So we know our supplier is going to be shipping the product in. We already had that information. Again, just to remind you, the information we had regarding the forecasts and the orders and stuff. So that sheet was earlier, just to jog your memories, if you will. But now we can start to populate that. We've got our forecast orders and the actual orders coming in from the customer, and similarly forecast and actual demand going out to the supplier. In addition to that, we've got to lay in our internal production schedules. So, or typically, all of the different areas are scheduled separately. Interesting to note here, just want to draw your attention to it, these glasses. So what generally happens in most organizations is that the schedule may be issued, but the reality is it changes from day to day, if not indeed from hour to hour. So those sunglasses are what we call go-see scheduling, and typically will supplement the proceduralized schedules that are issued generally on a weekly basis. I want to highlight then on the next one some key issues for you. So first of all, this item up here, let me just enlarge this. This is 920 pieces per day. We basically know, based on the working time, the number of days, and the demand level that we were already given, that the customer is on average looking for 920 pieces per day. So a really important piece of information, because armed with that information, we can now go and we can start to look at the inventory levels that we've identified at each of the stages, or between each of the stages. So between stamping and welding, we identified a total of just 7,000 units of inventory, left and right combined. So 7,000 units of inventory at a daily demand rate of 920 pieces per day equates to 7.6 days worth of inventory. So essentially, if this inventory is sitting here, it's going to take 7.6 days of pulling that away at the rate of the customer before I need to move another piece in here to satisfy demand. So effectively, if more material arrives in at the start of the process, the time it will take to get through that process is essentially the 7.6 days plus the 5 days for that coil, and then the equivalent days inventory of all of the additional inventory points that we had in that line. So effectively, what we can now do, based on the 920 a day, understanding the demand of the customer, in other words, we can now put a time value onto the inventory that's sitting between all of the processing activities. This is a key piece of being able to do that flip, if you like, from numbers of units to actually calculating an inventory lead time, if you will, allows us to construct the bottom piece of our value stream map, which is essentially the timeline. And if you look at that, what you can see is we've got our 5 days worth of inventory. We have a second, which is the processing time for stamping. This line, as you'll see, is up, down, up, down. It's at the high and lows, and the high values are the non-processing time, static or dead time, and the processing time or value add time is calculated on the lower level. So we have our 39 seconds for weld, our 46 for the other weld, 1.8 worth days inventory sitting in between, and similarly we work our way along. Ultimately, that then allows us to identify that for this particular value stream, which contains a processing time of 166 minutes, or 188 seconds, I'm sorry. That's all of the processing time, the sum of all the different steps that are in it. Yet it takes 23.5 days for the inventory lead time, for the lead time of the material arriving in to work its way through. So if a customer has a change, or if there's a spec change in the material, for example, we're sitting with 23.6 days of that customer's requirements in our works before we can introduce that new material change. Okay, so essentially what we've done is we have constructed a current state value stream map. Using the data that was there, the key step, if you will, is to be able to understand what the customer demand is, and knowing that, to be able to take these inventory levels and convert them into time values. And as you can see, processing time 188 seconds, yet a lead time of 23 days. So we obviously want to make that a little bit better. Need to think then in terms of what we're going to do to make that better. And essentially, we're now going to pull up another set of slides, and I'm going to talk you through some of the guidelines that come into play, if you will, when we're about to create the future state. So essentially, before we jump into doing the future state, just want to talk you through some of the things to bear in mind, some of the things to be aware of, and some of the things that we should be trying to improve or resolve as part of constructing the future state. So this is part of the perfection model, if you will, as well, where we're looking to make things better. There is a school of thought which says that before you create your future state, you should actually construct an ideal state. In practice, though, many organizations tend to do the future state on typically an annual basis. So an ideal state may be a useful activity, but on an occasional basis. But the general cycle of value stream improvement tends to be from current state to future state, implementation, new current state, then develop future state again, and into that kind of annual cycle. So in terms of constructing the future state, we've got all our data. We can see where there are some opportunities, but there's a number of problems that we need to focus on. The most obvious one that we need to think about is that this map that we constructed is for a very classic mass production model. Each area is being independently scheduled without any cognizance or attention being paid to what's happening in the earlier or the later processing steps. So this kind of island mentality permeates through it. Ideally, what we want to do, you can see on the bottom of this diagram that we have here, is we really want to make more product, and we want to be able to get it through that process more speedily, And if we can improve the quality while we're doing it, well and good. But really, we want to get rid of these disconnected islands that are all independently scheduled and totally unconnected. Thing to remember again about waste, we've talked about that previously, but it's only a symptom. So we do need to get behind the problems and develop solutions, countermeasures for the particular issues that we're encountering. And again, you get a sense of this as we work through the future state map. Again, one of the key things to bear in mind about value stream mapping and about the lean approach is that we're looking for the systems benefit. We look at things from a holistic or a systems perspective rather than from the individual steps and processes that we might have within that system. So again, we're not looking to maximize individual steps within the process, and potentially that's done quite typically actually at the expense of the overall process, or certainly not delivering any benefit to the system. Okay, so that's another factor to bear in mind. TAKT time. TAKT time is very important. We've covered it as part of standard work. However, it is a really essential piece in terms of figuring out our labor requirements within the value stream. And again, you'll see an example of that as we construct the future state. So we need to understand how much time we have to satisfy that daily demand, those 920 pieces. And based on that, we can develop our cycle times and figure out our production process. Another question we might want to think about is, do we build to shipping and just build it and ship it, or do we actually want to have a supermarket there? The answer typically will depend on the volatility of the variation in the shipments to the customer. So if it's a very steady, stable environment, not a whole lot of value in terms of putting a supermarket in. However, if you see volatility from a day-to-day or from a week-to-week basis, then it may well be worth putting a supermarket in. Or if you have variations in models or styles, that potentially could be accommodated by using a supermarket as well. So again, another question, if you will, that needs to be borne in mind and thought through in terms of designing the future state. Obviously, another key one is flow. It's our third lane principle, and obviously, when we look at the map that we've constructed, we can clearly see that there are major breaks in that flow and that they are consuming significant amounts of time. So we want to try and make the product flow through the process a bit more effectively and stop all of these quantities that are waiting. Again, if we look at the figure that's on your screen, if you're moving stuff through in batches, then typically there's the time to manufacture the batch, which is a multiple of the individual time, followed then by any storage time before that batch gets worked on in the next process. So, you know, while normally it could be 30 minutes to get a batch of 10 wood pieces of 1 minute each through that system, in reality, it typically would take a lot longer. Whereas on the bottom here, if we can move that piece snappily, one piece at a time through, then we can get a first piece out in 3 minutes and potentially a batch of 10 in 12, as opposed to the 30 plus that typically will happen in a more traditional push environment. So again, flow, we want to try and embed flow into the future state. The other things relating to flow is, I suppose, you know, where do we schedule? How do we manage that? And there's basically a choice to be made. Do we want to have a push system? Sorry, I beg your pardon. Do we want to have a series of Kanbans where the flow is disconnected? We certainly want to break that push system. So we need to be thinking about, where do we want to schedule? What point in the process, and how do we organize the movement of materials in front of and behind that? One of the tools we can use for that is the idea of a supermarket. We'll get into more depth in terms of structuring and working these. However, the basic concept is that as material is sitting in the supermarket, when there's a requirement, for example, to ship, material is withdrawn. The paperwork that's attached to it is sent back into the area that manages that supermarket, and they basically will replenish the stock. Very similar to the true supermarket model. So that's one option we have. And you can see that there's another example here showing how it operates. And why would we put this in place? Well, for example, if there's batching by volume fluctuations, if there's long changeover times, or if there's significant distances between where two processing steps might be located, they're all reasons why you might put supermarkets in place. So again, something to think about. So where do you schedule? You want to get away from this multiple scheduling, obviously. And if we put supermarkets in place, or we use FIFO, then theoretically we should be able to schedule in a single point, and the movement of material is triggered into or out of that point based on the customer demand. So we'll see that in the future state, but again, it's a question to be answered, if you will. The other issue to bear in mind is that we don't want to have long runs of single products. You want to try and get mixed production. So in this example, we have left and right components, which we don't want to make all of the week's lefts and then suddenly then flip over and do all of the week's rights. Why not? You may ask. Good question. And let's work through this panel here. So if you identify that we had, for example, 500 A's here and 500 B's and 2, 4, 800 C's, and then we're back into the A's again. So this system is make all of the A's, then make all of the B's. The issue with that is that if a customer contacts us after we've made the A's looking for an additional quantity, then they're going to have to wait until the following week. An alternative would be if we could make a daily proportion of A's, a daily proportion of B's, and a daily proportion of C's. Then if the customer orders, we can quickly we can satisfy that demand within a day or so. Now, the challenge in terms of doing that is fundamentally around short changeovers. So setup production typically has to be a significant part of the transition in most organizations from the traditional push environment into the pull environment that we're looking to create. Better again than doing it every day is if you could get your changeover times down to such a small time, you could potentially be doing a twice a day turn through the full cycle of parts. So lots of things to consider there. And again, before you start constructing the future state, you should give some thought within your own processes to the questions raised by that section that we've just gone through. So some of those questions were, what's the TAKT time? Do we build a shipping or supermarket? Where do we use continuous flow? Where do you have a supermarket? How do you level the production mix? So lots of questions to answer and think about. This piece down here, I particularly like. I think it's important. So what we're going to do is we're going to reconfigure the value stream into a more meaningful or a leaner operation. However, there's a whole load of work that's going to get generated, and there are supporting improvements. So while we're going through a value stream and we're developing a future state, ultimately behind that future state map, there needs to be a significant amount of work done to actually develop and implement the solutions that this new value stream map is dependent upon. And again, that will become clearer as we work through the next number of slides, hopefully. Okay, so we started out with our value stream map, or we finished our current state value stream map. So let's start out with a couple of items. Firstly, this stamping operation here that we talked about. Let me just open it up a little bit. Okay, so I'm looking at the 200-ton press. Remember, it's making for a number of different product families. So it doesn't just service this particular product family. There's a good reason for putting a supermarket in place. Okay, so it's not really going to be connected. So ideally, if you could visualize what we've got with the stamping machine is we have a supermarket beside it to feed this particular line. We'll have another supermarket potentially above it, and another supermarket out here, and another supermarket off here, all of which are servicing the different product lines that this particular machine manufactures parts for. Okay, so the concept is it's a shared service or a shared machine. It provides multiple products and multiple product production lines. And what we're doing is we're putting a store there, a supermarket shelf, and we'll pull from it and put a trigger system in place to drive the replenishment as the materials are used. Okay, so the other option is let's think about allowing for some variation in what the customer is going to be looking for. So we put a supermarket in here rather than build directly to shipping. So again, we'll put the supermarket in. The plan here is that we will fill that supermarket, and the shipping people will pull the product from the supermarket and out to the customer, and that then will trigger us to replenish that supermarket as it's required. So effectively what we've done is we've divorced or separated the shipping process and the stamping process from the rest of them, and we've put a supermarket in place. Effectively, that also means that we can eliminate this scheduling system that was there, And rather than the inventory that was sitting here, we will, as part of putting that supermarket in, we will establish a level of inventory, and we will manage it and control the inventory to that level. More about that later. Okay, so within the remaining processes, we've got my little stamp here at the 1 second, and it's doing a second for us and a second for various other people. So if we look at our welding and our assembly operations, the various cycle times that that we were given can be shown here against the TAKT time, which is 60 seconds. So we can already see that assembly 1, actually the time is too long. However, we can also see that there's an awful lot of wasted time in here. There's a lot of operator time being wasted. Plus, the work isn't balanced between the different assembly 1 and 2 and weld 1 and 2 operators. So there's a number of opportunities that we can look at in terms of making things a bit better there. Firstly, let's look at the 2 welding machines. So we had a weld 1 and a weld 2. If we try and close couple those machines and get to that point where we can get single piece flow perhaps moving between them, that would be wonderful. We take out the inventory that's sitting in between them. We'd only need to schedule possibly one of them. However, when we know the data and we look at the data sets that are that we've captured or that we were given, we can see there are some issues. So on the first welder, we have an uptime of 100%, which is great. However, on the second welder, we have an uptime of only 80%. Now, the impact there is if we bring those together and we're moving at a piece at a time, and one of them goes down, then effectively the 2 of them are going down. So we need to fix that uptime. In other words, we need to get the uptime on that welder up to 100% so that it's at the same level as the other, if we are to take out this inventory and get a single schedule. We'd also be looking at taking the 2 cycle times and balancing the work between the 2 so that the work has moved along. So while it looks nice to say, yeah, bring those welders together, and it is, there is quite a piece of work required, specifically this Kaizen burst, and that's the kind of typical notation that we use to identify where work is required. So we've calculated our TAKT time here. We know that they take them in units 20, so we sometimes talk about a pitch time, and that's that we need a tray going out every 20 minutes. Okay, fundamentally though, we looked at bringing these 2 welders together, allowing us to take out inventory, eliminate the schedule, close couple the work and get some better flow. However, we have a technical problem that needs to be fixed before we can do that. So let's move on a little bit. Why don't we do the same in the assembly area? Let's bring the 2 assembly areas together and let's take out that inventory and split the work across them. That's a no-brainer because there's no setup. They've got 100% availability, so it makes a lot of sense. Again, we can get rid of the schedule point, we can get rid of the inventory, and we have no technical work to do. That was easy, so that's a big benefit there, and we can get some single piece flow moving between these. However, the obvious question here, I have 187 seconds worth of work. So remember, if you recall, there was 188 seconds here. We took away the 1 second for the press. So within these 4 processes, we have 188 seconds of work. We know our TAKT time is 60. So theoretically, at least, we should need 3.1 operators. The model that we've put together requires 4. So the target would be to try and get to 3 operators. Try and reduce to get closer, because 3.1 is a lot closer to 3. If the number was 3.6, 3.7, then maybe you'd stay with 4. But to put almost an entire extra operator into a 3-person process is hugely wasteful. So we want to try and reduce that. Any ideas on what we might do? Here's some thoughts, for example. So you'll see I've got 165 seconds. What happened to the 187 you asked? Okay, good question. Keep that one in mind. In addition to that, I've split the work. So I have a TAKT time of 60. I therefore would like to have a cycle time of 55 seconds. And if I can get a process that consists in total of 165 seconds, and I can split the work evenly between 3 operators, each of them with 55 seconds of work, then the first operator does 55 seconds of welding. The second operator does the remaining piece of welding and the first piece of assembly. And the final third operator, if you like, does the bulk of the assembly and finishes it. So wouldn't that be nice? Yes, it would, but there's a lot of work required. So again, what I've now suggested, if you will, is that we take all 4 processes, let's join them all together. So what do we get? We get to take out all of the scheduling that's here. We get single piece flow moving through it. We get rid of all of this inventory that's sitting in there. However, there are issues that need to be addressed before we can do that. So look now at what was originally my uptime of 80% on the welders. If I want to bring all 4 of these together, I have a lot more work to do. I have that uptime still to fix. But additionally, because I've brought the welders and the assembly stations now together into a single piece flow environment, that changeover time of 10 minutes, if I stop my welders to do a 10-minute changeover, I stop my assembly process. So now I need to do a setup production activity to get that changeover down, down to a single minute ideally, single minute exchange of dies, another lean tool. So here now we have reliability and uptime that has to be fixed on one welder. We have a setup production program that's required on both of the welders. And also, by the way, we need to get the cycle time down from 187 seconds to 165. Now, that's not as difficult as it might seem, at least the cycle time piece of it. Specifically, if you think about the extra work that's often involved in handling batches of work, so putting them into baskets, taking them out of baskets, the handling systems, the stress, the work, when you get into single piece flow, you can often actually save time just by virtue of the fact that you've eliminated the handling requirements around the batch. Also, fixturing can be redesigned or simplified to take seconds out of it. So that it's a job of work that needs to be done, certainly, but not impossible by any means. So ideally, what we're saying here is that we have a future state, potentially here with the cell, if you like, of all these happening together. We have a range of specific activities which are going to happen, have to happen to enable that to become a reality. So what will that look like? We'd end up with a weld and assembly cell. Work content has to be taken down to at or under 165 so that we can split it into 3 packets of work and stay under the TAKT time. We have to do an uptime improvement on the second welder, and we have to do a changeover setup production on both of the welders. However, if we do that, those 3 technical pieces of work, if you like, then we have the wherewithal to actually have a single piece flow cell, a lean cell in here making the parts, a supermarket feeding the raw stampings in, and a supermarket for the finished pieces from which shipping will take their demand. Essentially, we now have very little inventory in place other than the supermarkets. So what do we do with the supermarkets? You can see on the right-hand side here the 2 days under the supermarket. So essentially, setting the initial supermarket value is an arbitrary number. You take a safe number to minimize or eliminate the likelihood of stockouts. So on the basis that there was a daily replenishment going to the customer, we reckon that let's put a 2-day supermarket in there so that even if this line stops for an entire day, we'll still have a buffer of an additional day. And we didn't envisage that that's going to, that type of stoppage, or that anything greater than that type of stoppage is going to occur. So we put 2 days in there. Now, again, the reality is that there will rarely be 2 days in there. The only time there'll be 2 days is literally before that truck pulls away. After the truck pulls away, you're down to a day, and then that stock gets rebuilt back up until the delivery truck comes and takes it away again. So we count that inventory as 2 days, when in fact the reality is that most of the time it will be significantly less than that. Similarly, on the stamping press, we're going to use a slightly different system. This is a signal Kanban rather than a production and withdrawal Kanban. And again, we'll cover that in other lectures. But essentially how this works is as the stampings are used up and taken out of the supermarket, the cards effectively are gathered together, and when they reach a certain batch quantity, then they're fed back into the stamp, and that will cycle through its quota, if you like, of parts for this line. Again, the information that we had is that that stamp would typically run every day. So by putting a day and a half or 2 days inventory in front of the stamp, that again gives us plenty, and the same rules apply in terms of how it would run down. So essentially what we're now going to look at is we have our supermarket with 1.5 days stock here after stamping, and with 2 days stock. And while those levels will rarely be reached, that's the max level, that's the number we're going to use in any calculations. Between the weld and the stamping, you can see that as we take stuff from the stores, these cards go back, batch there, a triangular card, which is the symbol for a single Kanban, and that's replenished basically on a daily basis. Similarly, on the other side, we have these 46 trays are being pulled with 20 pieces in it each day, being loaded and taken out. And as those parts are pulled, these Kanban cards are being taken off them and fed back in here so that this area will replenish them. All very well and good. However, there are some additional controls that we also would want to put in place in here. So what have I done? If you have a look at this OXOX up at the top, what essentially we're going to do is we're going to make sure that we don't take all of the left cards and then make all the lefts, and then in the afternoon do all the rights. We want to continue to make the mix in the cell in the same ratio as the mix is being taken out by the shipping area and shipped to the customer. So what we basically do is we put a Junke system in place, and there are notes again available on that separately on Moodle. And what that does is it replicates the ratio of parts. So if the customer was taking 2 lefts to 1 right, if we look at the number, it is roughly 2 lefts to 1 right, 12,064. So ideally, what we'll do is we'll schedule the sequence back within that cell to build a left, a right, a left, a right, and basically replace that system rather than build all of the lefts and then all of the rights. So that's a Junker board, and that maintains that product mix that we want, reflecting what the customer requires. Okay, so essentially there we are. We've got a supermarket here. We've put our cell in place. We've got another supermarket here. And the last step we might do is put a supermarket in front of the stamping area. So rather than these deliveries, we'd put a 1.5 day supermarket and work a deal with the supplier to come and replenish it as it's required. So we now have pull in as required into the stamping area. That work is triggered by the pull from this supermarket into the welded assembly area. And that work is triggered by the pull out of this supermarket into the staging area. And we have a replenishment system, single piece flow, and we've eliminated all of our scheduling. We've taken a huge amount of inventory out of the system. So let's have a look at what the timeline looks like now. We've still got our 1 second. We've taken this down to 165. So in terms of processing time, we've taken it from 188 seconds down to 166. No significant difference. However, we've got 1.5 days maximum inventory sitting in this supermarket. We have 1.5 days maximum inventory again sitting here. And we have 2 days inventory maximum sitting here. So we have a maximum of 5 days. And we can reduce that over time as we get more confidence in the stability of the processes that are delivering that. So effectively, what we've now got is we've got pretty much the same cycle time. We've made some minor reductions. We've balanced the work. We're now down to 3 operators. We've taken out a huge amount of inventory. We're responsive within 5 days to the customer. And we've basically got quite a lean cell in place, and a value stream that's pull rather than push based and is far more responsive to the customer. And that basically is the end of the tutorial on constructing the future state map. Thank you for staying and listening, and I hope that you enjoyed it and found it useful.